or your goal for the day, is to be able to graph quadratic functions, put them all the way close. Graph quadratic functions in standard form. Okay, but to kind of get us thinking math a little bit here, let's talk about symmetry for a second. This is kind of interesting. This will come into play today, but this is sort of a little bit of a tangent, just a little bit. So let's talk about different kinds of symmetry. Let's think geometric symmetry for a second. Go back to geometry class and tell me what's one kind of symmetry that square has. Okay, bilateral symmetry, vertical symmetry. I think you guys mean the same thing, maybe. I think both those answers are getting at line symmetry, right? So can anybody tell me what is one axis of symmetry or line of symmetry?
Diagonal.
Okay, so we'll start with a hard one. So there's one right there, isn't there? If I fold this shape across that line, it overlaps perfectly. Okay, how many total can you find?
3 and 4.
What's it gonna be?
1, 2, 3.
There you got them all right there. I saw them all. So there's one, there's one, there's one, there's one, right? Okay. Any other types of symmetry that shape has? It has rotational symmetry. Good. If I were to put a tack, cut out this square out of cardboard and put a tack in the middle, I could spin this thing through a quarter turn, or I could spin it through a half turn, right? Or I could spin it through even 3/4 of a turn, and it would overlap perfectly. So it has a whole bunch of symmetry that way too. Can you think of a shape that has more symmetry than that? Circle. Okay, circle. Now, a circle is kind of a bizarre one, isn't it? Think about a circle. Yeah, how many lines of symmetry are there on the circle?
All the way up.
In fact, what would the answer?
All real.
Infinite number of lines of symmetry, right? Because there's one. There's one. There's another. There's another. I could just rotate those through infinitely small angles and get an infinite number of lines of symmetry, right? How much rotational symmetry does it have? How many angles are there that I could rotate that thing through? Infinite, right? So a circle is really the ultimate symmetrical geometric shape, isn't it? Okay? So we talk about symmetry a lot in math. Symmetry is important because what it does for us, practically speaking in math, is a lot of times it allows us to cut our workload down quite a bit. In my calculus class, we're just getting to a section where we're starting to do what's called curve sketching, where we take some function and we apply calculus to that, and we want to be able to sketch the curve, meaning we want to be able to identify all the interesting places on the function, where it has turning points, which we'll actually talk about today. We're looking for maxima and minima. Maxima is just plural for maximum, minima is plural for minimum. Those are all vocabulary words that will actually come up in our Algebra 2 class today. One of the things we do, though, we get pretty complicated functions, is calculus, a lot of it's about getting the answer the easiest, most efficient way. And a lot of times we can take advantage of symmetry to do just a portion of the graph and then harness the fact that there's some symmetry and do some reflecting and rotating to get the rest of it for free, right? And that's something we do a lot in math. We even do that and there's some kind of bizarre applications of that. Have you ever thought about time symmetry? It's here. Okay, here's an example, real simple example of time symmetry. I'm not going to go into too much detail. So just imagine, you got to kind of use your imagination a little bit here. So I've got a ball in my hand, I'm going to throw the ball up in the air. I'm going to videotape this. Have we talked about this?
Yes.
Oh, we already did this? Okay. So we already talked about, well, no, but you get the idea that so my point is just that we already did this example. I could use a refresher. The ball looks, it's a mirror image. The upward trip of the ball to its apex is a mirror image of the downward trip of the ball back to your hand. But a mirror image in what sense? A mirror image with respect to time, right? The path up and the path down are the same. Okay. Did I even show you a little graph of this?
You did.
I did. Okay.
Did not.
So I did not. Well, here I may have, but here it is again, real quick. So if we were to do something like this, like if we're graphing time on the horizontal axis, and we're graphing height on the vertical axis, and we'll just call it y for height. If we were to graph the height of the ball as a function of time, let's say it's gonna pop up from ground level. It's just gonna get smacked from the bottom and pop up from ground level and then fall back into the ground again. The path would just look like this. Okay. Now, this isn't supposed to be the path of the object in the air. This isn't a map of the projectile motion or something. This just means this is the height as a function of time. It starts off, the height is changing really rapidly because it's moving quickly upwards, right? But as it moves up, it slows down, gravity slows it down. And it gets to a point up here where it gets its maximum height, and then it picks up speed and heads back toward the ground. And towards the end, it's decreasing its height pretty fast as the time changes. Does that make sense? Like, for example, like if these are 1 second increments, we see that in the first second, the ball goes up quite a bit, right? In the second second, it doesn't go up as much. In the third second, it doesn't go up very much at all. And then in the fourth second, it barely goes up at all, right? You see my point? Okay. But then on the way down, it reverses all that. So you get this time symmetry, right? And so it's symmetrical about the center of that time distribution, right? So the trip up, from tossing it up to getting to the apex, is a mirror image of the trip down if you graph the height as a function of time. Very interesting. Okay. All right, so for today, we're gonna look at some symmetry too. We don't go into nearly that much depth, but I want you to see that this stuff, it comes into play often in math. So go ahead and fill in some blanks on your notes here. We're gonna look at the standard form of a quadratic. We should call this a function, not an equation. So cross that out. Standard form of a quadratic function is f of x equals ax squared plus bx plus, what do you think? C, you got it. Ax squared plus bx plus c. And we'd say that a and b and c are just parameters, meaning they're just special numbers. They're numbers we would plug in to dial in a specific parabola. In much the same way that if we were to graph a line, the parameters would be m and b. Typically, we write lines in the form y equals mx plus b, right? And if we pick values for m and b, we can graph any conceivable line in the xy plane. Same thing here, by picking specific values of a, b, and c, we can make any possible parabola in the xy plane, okay? And incidentally, that's a parabola, by the way, what we just graphed there. If you look at the height as a function of time of an object that you're throwing up in the air, it makes a parabolic shape in the plane defined by height and time. Okay? So what about parabolas? Let's talk about these a little bit. They come up a lot in math and in physics and science. A quadratic function always is going to give us the shape of a parabola, or a parabolic shape, which is like a U-shaped curve. If the coefficient of x squared, which we call a, if that parameter is positive, then the parabola always opens up. If it's negative, the parabola always opens down, okay? Let's look at the anatomy of a parabola for just a second. This, what do you think? Has it got symmetry?
Yes.
What kind of symmetry? Bilateral line symmetry, right? So it's got line symmetry in the vertical line that we call the axis of symmetry is just a vertical line that goes through, splits the parabola evenly in two. What do we call that point that's either going to be the maximum or the minimum of the parabola? What do we call it? What's the name of that point? In this case, the coordinates are -2, 3. Can you remember what we call that? It is a turning point, but more specifically, the word I'm looking for here is vertex, right? So the vertex of a parabola. Now that's not like a geometric vertex. A vertex in geometry was always a sharp corner, right? Well, when we talk about parabolas, we still want to use that word because it's a really important point. It's kind of it's sort of like the point of the parabola, only it's not very pointy. It's kind of blunt, right? So there's our vertex. We've got this axis of symmetry. The axis of symmetry will always pass through the vertex, and it's got this folding symmetry. If we think ahead a little bit, our goal for today, our main goal for today is going to be, can we graph these things, right? Well, how do we graph functions? If you think back to Algebra 1, a lot of times when we graph functions, we just want to make a t-table and pick some points. We'll plot some points and then connect the points to create the shape, right? Remember doing that in Algebra 1? Okay, well, we're going to do the same kind of thing today. But I want you to think how you could harness symmetry to your advantage here. Yeah. How could we use symmetry to graph this parabola and use it to our advantage? What's probably the most important point that we always need to find if we're graphing a parabola? The vertex. Yeah, we got to find the vertex, right? And then how are we going to get the rest of it? We know it's kind of a U shape, but the parabola could be stretched out vertically. It could be kind of compressed. We need to be a little more specific than just saying it's a parabola. We got to be able to maybe define the shape a little bit by picking some points, right? So we could, for example, if we calculated the vertex was here, we could calculate a couple other points. Like maybe we could calculate the fact that it goes through this point right here. We could find the coordinates of that point using our t-table, right? And maybe I could even get a second one if I wanted to. Maybe I get one down here also. Okay. Do I have to go find 2 points on the other side to graph this thing? Here's my question. What can I do? John, what can I do? I can reflect those points, right? So I can use symmetry to cut my work in half. Once I find a point on one side of the axis of symmetry, I can always just reflect that over the axis of symmetry to get a corresponding reflected point on the other side, right? And then 2 for the price of 1, right? And then I can just connect all those smoothly and make my parabola, okay? All right, so how are we going to do this stuff? Well, the axis of symmetry, the way we find that, there's a formula that allows us to find that. Here's the formula. The axis of symmetry formula is x equals negative b over 2a. Okay, and that really gives us 2 very important things. That tells us the x-coordinate of the vertex, but that's also the name of the vertical line that forms the axis of symmetry. Because what's the definition? How do we write a vertical line? Those are really simple. We write a horizontal line to be like y equals 5. Right? And then it's just going to be a horizontal line where the y-coordinate is always 5, so it cuts through the y-axis at y equals 5, right? How do we name a vertical line? X equals some number, right? And so whatever this number is, it's going to be the equation of the line, but it's also going to tell us the x-coordinate of the vertex, isn't it? So we're really getting 2 things for the price of 1. These are pretty good deals we're getting in this section. A lot of 2-for-1 deals here. And then once we find the x-coordinate, somebody quickly remind us, how could we find the y-coordinate if I have a function and I know what the x-coordinate is? What do I always do? If I know the x value, to find the y value, what? Like for example, there's my function. What if I know that, well, let's do this one. Let's just practice a little bit here. Let's find the axis of symmetry first of all. What's my formula? X equals, do you remember? Negative b over 2a. Well, we got to identify what are a, b, and c for this one first of all. So what's a in this function? Negative 2. Good. What's b? Tricky. 0. How come? There is no x term, right? So the coefficient must be 0 because it went away. So b is 0, and what's c? Okay, so there's a, b, and c. So now we can just plug that stuff in, right? So we get, here's how I like to do this. If b is 0, well then what's negative b? I mean, in this case, 0 doesn't even have an opposite, right? It's its own opposite. So I get 0 divided by, who cares? 0 divided by anything is what? 0. So on the bottom, we technically would get 2 times negative 2 is negative 4. But our axis of symmetry is just going to be x equals 0, right? You know, if I want to find the vertex, the ordered pair that's the vertex, I'm halfway done. What's the x coordinate? 0. Yeah, it's 0, right? Because whatever the axis of symmetry is, you know, in this case, the axis of symmetry would just be the line x equals 2, right? How come? Well, because, or negative 2, sorry. Right, because that's the x-coordinate of every point on that line, including the vertex. They all have an x-coordinate of negative 2, so that's how we name the line, okay? So here we're going to get, for sure, x equals 0, right? That's the x-coordinate of the vertex. How do I find the y-coordinate? Plug it in. F of 0 equals negative 2. I'm going to open a set of parentheses to plug something in. Plugging in 0, and what do I get? What's negative 2 times 0 squared? 0 plus 7. So f of 0 equals 7. So that's what goes there. What do you know? Okay, get the idea? Okay?
We got this circle.
Oh, yeah, yeah. Okay, and tell me that too. Does this have a minimum or a maximum? Well, what do you think? How do you know? It's going to be a maximum. How do you know? Okay, because, well,
No.
that's not why. Now, we haven't talked about that part yet, so let's go back and talk about the minimum maximum stuff. So we know in math, the vertex for a parabola is always going to be what we call a turning point in math. Turning point meaning, what's it mean to be a turning point? Like if you say that was the turning point of the game, what happened in the game? Things changed around, right? That's when the outcome became determined. You know, that's when the team went ahead and they won the game, right? So, turning point is where things are changing directions, right? So, when we talk about a turning point for a parabola, think of it this way: if an ant were walking along the parabola from left to right, that's going to be the place where the ant would transition from walking uphill to downhill, or if the parabola opened upward instead of downward. Then, so the turning point was down here, then it would transition from walking downhill to uphill, right? Now, what are the names we would give to those things? What would I call this kind of a turning point here, my vertex? That's going to be a maximum because it's the highest possible value. What would this be? That's a minimum because it's the lowest possible value. In math, conveniently, maxima, and that's the plural for maximum, maxima are always just peaks. They look like mountains, right, when you look at the graph. And minima always look like valleys, okay? All right, I think we got it covered. So then you can tell me, oh, and we already know that when A is positive, the parabola opens up, right? When A is negative, the parabola opens down. So a positive value of A will always give us, what, a maximum or a minimum? Positive value of A.
Minimum.
Always a minimum, because it's always going to open up, right? And a negative value of A will always give us a maximum. Good. So then what's this going to be?
Max.
It's got to be a maximum because we know A is negative. We know that this parabola is going to do that, right? So it has to have a maximum. Yes, sir?
So, do we plug like the values in for the axis of symmetry right there?
Yes.
Okay.
Mhm. Yep. Yep. Let's do another one. Let's do some examples. This is the stuff we really want to get you able to do well today. So what about this now? Values of A, B, and C. What's A? You got 1, right? Coefficient of x squared. What's B? Negative 8. What's C? There you go. Okay. And the axis of symmetry formula is just what again? Okay, so if B is negative 8, what's negative B? Positive 8, good. Over 2 times A, which is 1. What's 8 divided by 2? Okay, good. So we get the axis of symmetry is x equals 4. What's that tell us about the vertex? What's 4?
X.
The x coordinate's 4, good. Okay, to find the y coordinate, what would I do? Plug it in. So I'm doing f of 4 is going to equal 4 squared minus 8 times 4 plus 9. What's 4 squared? Minus plus 9. So that's going to give us 16 minus 32 is negative 16 plus 9. Negative 7. Okay, so we know f of 4 equals negative 7. And so there is the y coordinate of the vertex. Minimum or maximum?
Minimum.
Minimum, good. We know A is positive, right? A is greater than 0, it's positive. So that has to be a minimum. Got to open up, right? Okay. All right, what about this guy? So now we're going to go a step further. Now we want to know, what's the graph look like? Okay. So this is number 5 on your notes. Okay, this time, what are the values of A, B, and C? A is what? B is 0, C is 0, okay? So let's find the axis of symmetry. X equals negative B over 2A. Let's always write the formula down. Now we can plug some stuff in. So what do we get?
Zero.
0 divided by, who cares, right? I guess it's negative 6, but we get an answer of 0, right? So what's that tell us then? That tells us this, that the axis of symmetry is x equals 0. What's that line look like? Vertical line through the y-axis at 0, so that's really just the y-axis, isn't it? Right, so here's our axis of symmetry. There's the line x equals 0. And now to graph this thing, we just need some points. We've got to start with the most important point, which is the vertex. What can you tell me so far? X is 0. And y is, we can do this one pretty fast. If I plug 0 in, I get 0. So I get the point 0, 0, which is right there. And I'm going to put that on my t-table. Okay? Let's just record all of our points on our t-table. So one of them is, and I'm gonna put this one in the middle, and you can tell me why in a second. So I'm putting x equals 0, y equals 0. When I make a vertical t-table, remember, that looks just like an ordered pair, doesn't it? Okay? So now to define the shape of this thing, we just need to pick a point or two on one side of that axis of symmetry, and then I can reflect those points over to get the other side for free. So how about the point like 10? Does that sound good? I could do that. If I plug 10 in, what am I going to get? Negative 3 times 10 squared.
30 square.
Well, hold on now. I got to use order of operations, right? I have to do the exponent first. So I'd square the 10 first before I multiply. So what's that going to be? Negative 300, right? Negative 3 times 10 squared, which is 100. Well, that's a terrible point for my graph. Way too big, right? Yeah, I want to pick something. I want to pick something closer to home. Meaning, I want to pick something closer to that axis of symmetry. Because if you think about the shape of a parabola, they're nonlinear, right? Which means they pick up speed in this case. As we move further and further away from the vertex, the walls of the parabola get steeper, right? And so it starts to be more dramatic. You get really big changes in y. So we want to stay close to home where we get nice convenient numbers to pick, right? Okay, so let's pick 1. If I pick 1, what's f of 1? Negative 3 times 1 squared, right? So negative 3. Yeah, good. Well, let's keep track of these. F of 1 equals negative 3 times 1 squared, which is negative 3. So over 1, down 3. Okay? Let's maybe pick one more over on the right side. How about 2? But even 2 is not going to work well, is it? If I put 2 in, look what happens. What's negative 3 times 2 squared? Negative 12, which is off the charts down here somewhere, right? So this is a pretty steep parabola. What do you think that that value of a did to our function? A is negative 3 this time. The negative means it flipped it over so it opens down. What did the 3 do? It
Vertically
stretched it out vertically, didn't it? Right? And we'll see that on the shape of the curve. So now, I could get these other points for free. What's going to be the mirror image point of that one? I want you to think about this. Negative 1, negative 3. Everybody see that? How come? Because the distance between 0 and 1, the horizontal distance is only 1, correct? Okay, so that distance is 1, which means that that distance also needs to be 1, doesn't it? It needs to be 1 to the left if the other one was 1 to the right. 1 to the left of 0 is negative 1, and I know the y-coordinates have to be the same because they're mirror images, right? So there's that one. What would the other point be? What's the mirror image of this one? Negative 2, negative 12. I don't really even need the t-table for those, though, do I? Because I've got the points right here anyway. Now all I've got to do is just connect the points in a nice, smooth parabola. Okay, and there you have it, man. There's our parabola. Okay, make sense? Okay, so now what about the domain and the range? Let's talk about that. The domain, X or Y values for domain. X values. So what's the domain of this green parabola? The domain.
Y is greater than less than negative 2.
So, what do you think? Okay, how come?
Oh,
You're right.
Yeah.
Because if I zoom out, it goes forever to the left and forever to the right. Agreed? So if I were to project this onto the x-axis, the whole infinite parabola, it would cover the whole x-axis, right? Okay, so the domain is all reals. What about the range, though? You have to be a little more careful with the range.
Less than or equal to 0.
Okay. Less than or equal to 0. And the reason it's less than or equal to 0 is because that 0 is important. That 0 is the y-coordinate of the vertex. Everybody see that? Isn't that always going to be the case? If you look at any parabola, let's go back to this page. This one right here, the vertex is a maximum, and so the range is going to be all of the y values less than or equal to that y value, the y value of the vertex. If the parabola opens up, then the range is going to be all the y values greater than or equal to that y value of the vertex. Right? Everybody with me? Okay. Good. So we got this. So then let's try another one. This isn't so bad, is it?
No.
Let's try that guy.
That's easy.
Okay, so we need A, B, and C first of all. Nancy, what's A? 2. Good. While you're at it, what's B?
8 or
Negative 8. Good. And C is 6. Okay, very good. So then, yeah, that's fine. So what's my equation for the axis of symmetry?
X equals B over 2A.
Negative B
Oh, yeah.
over 2A. Good. And so if I plug values in, if B is negative 8, what's negative B?
Easy.
8. Good. Over 2 times A, which is 2. What's 8 over 2 times 2?
0.
2. Okay, 8 divided by 4 is 2. Good. So we get the axis of symmetry is x equals 2. Okay, so there's going to be there's my axis of symmetry. Good. So my vertex, I'm going to put a V for vertex. The x-coordinate of the vertex is 2. To find the y-coordinate, I'll just plug that in. f of 2 is gonna give me what? What's that term gonna be if I plug 2 in for x?
8.
8? How about that term?
Negative 16.
Okay. So 8 plus 6 is 14 minus 16, what's that give me? Negative 2. Okay, so my point, my vertex is going to be at positive 2, negative 2, so it's right there. Are you agree? Okay. So now, what are some possible choices? We said we want to stay fairly close to home. So what are some choices for x values we could plug into our t-table here?
3.
We could do 3. Okay. What else could we do?
1.
We could do 1, or we could do 4, I guess, or we could do 0. That make sense? Okay, they're all going to work. But in math, we want to, we're getting to a point now where math is getting sophisticated enough for us that it's always going to pay to just pause a little bit. Don't rush in here. Think logically about this. Is there a value of x that would be particularly easy to use? Let me ask you this. Do I want to pick points, 0 would be the easiest, wouldn't it? Do I want to pick points to the left of or the right of the axis of symmetry this time? Probably the left, because I'm getting smaller numbers, aren't I, that are easier to plug in. So you don't always have to go on the right side like we did last time. We could go on the left side. 0 is really easy. If I plug 0 in to my function, what do I get?
6.
Yeah, I get 0 minus 0 plus 6, don't I? So I get the point 0, 6. So 0, 1, 2, 3, 4, 5, 6. There it is. 1's pretty easy also if I plug 1 in. 2 times 1 squared is... No, you got to follow order of operations, right? This happened a couple times. People, let's review this real quickly. I want to make sure we remember. If I do order of operations, and I'm simplifying, I go top down, right? So I have to do exponents before I do multiplication. So f of 1 is going to be 2 times 1 squared, see what I'm saying? Minus 8 times 1 plus 6. Well, I've got to square the 1 before I multiply by 2, don't I? Right? So I get 2 times 1 squared is just 2, right? Minus 8 times 1 is 8, plus 6. So 2 plus 6 is 8, minus 8? 0. Okay, so we get the point 1, 0. So right there. And then I get the others for free, don't I? I can just reflect those over. And you see the relationship here also. If that distance is 2, then that distance has to be 2. If that's 1, then that has to be 1, right? And so we get these points over here for free. What are the y values without even looking at the graph? What's the y value that has to go with 3?
0.
Has to be 0, doesn't it? Because look, those two go together. What's the y value that goes with 4?
6.
Got it, is 6. So I don't even probably need to put those in my t-table, right? I've got them on the graph. And then all I'm going to do is just connect and extend. And there's my parabola, right? Okay, what's the domain? Boring. All reals. What's the range? Y is greater than or equal to or less than or equal to?
Greater than.
Greater than or equal to negative 2. There it is. Okay. All right, so I'm going to skip this example. So we can, when are we out of here?
3 minutes.
3 minutes. Oh boy. Okay.
2 now. We sign up.
I tell you what, we'll do this start class tomorrow.
Cool. We got pretty far.
Okay.